Okay. Hello, everyone, and welcome to today's webinar, co-organized by the Canadian Institute of Mining, the Rock Mechanics Division of the Canadian Geotechnical Society, and the Canadian Rock Mechanics Association. My name is Stratos Karampinos, and together with Jonathan Aubertin, we're responsible for organizing this webinar series. It's my honor today to introduce today's presenter, Brad Simser. Brad began his career in 1990 in Welcome, South Africa, working in underground rock engineering with Anglo American. He has been with Noranda, Falconbridge, Xstrata, Glencore Group since 1995, working at Brunswick Mine, Noranda Technology Center, and since 2003, the Sudbury operations. Today, Brad leads the ground control program of Glencore's Sudbury operations. Brad holds a bachelor's in geotechnical engineering from Queen's University and a master's in mining engineering and rock mechanics from the University of Witwatersrand. With that, I will now turn it over to Brad to begin his presentation.
Thank you. Okay, I'm just going to make sure this is working. Yeah. So today I'm going to talk a little bit about the art of ground control, kind of an observational approach to ground support design. I'll talk a little bit about some of the ground support design methodologies out there, but at the end of the day, I think there's still some areas that are hard to quantify, and you know, so any design numbers you come up with, and in today's world, you'll have a corporate auditor if you work for a big company who wants to know your design rationale and sees the numbers, and you'll have regulators that want to see the numbers. But the truth is, the numbers are just kind of an estimate. There's a few things that are difficult to quantify, and that's where at least grounding, you know, whatever your design is based on observations, empirical experience, is still part of the process. If you're in a new mine and you know you don't have 100 years of mining experience like we have, say, in Sudbury Camp, then maybe it's benchmarking with other operations and similar depths and similar rock types. But at the end of the day, there's still good old observations and boots on the ground and taking photos, and all that stuff is really still important. You'll see, I'll show some successes, some failures, and what I think are some of the gaps in the current ground support design. The gaps, I think, can be, you know, filled with some intelligent assumptions and estimates and things like that, but then, you know, it's not always a precise 2 decimal place number that can go into it. You'll see there's a bit of a bias. I've been in underground mining since 1990, but really been in hard, brittle rock with seismic issues. So, you know, buckling, squeezing ground, you know, might be different, or shallow mining's different. But so there's a little bit of a bias towards hard, brittle rock. And what I mean by, you know, observational approach, empirical is maybe not exactly the right word, but you know, you can see in the photo here, the upper shoulder, you wouldn't eat your lunch under it, but it's holding in place. It's where there was strapping and yielding bolts put over the original support system, and where the strapping stops, that's where the fall of ground occurred. And that type of observation is important. And so whatever design numbers you come up with, you need to kind of truth it and ground it in reality. You'll see I'll bounce around from, you know, quite a few years ago to more recently, and the photos. And so, you know, my old camera used to put the date on the photos, my new camera doesn't. But you know, you see a fall of ground or a rock burst incident, and of course it triggers an investigation, and there's a lot of things to consider, and these things aren't always easy to put numbers to. So you know, one of the first questions you might ask if you see this picture is was it a rock burst or a fall of ground? Gravity would put that material there, and a burst would as well. If it comes from the wall and it spits out sideways where gravity couldn't put it, then it's clearly a rock burst. If it comes from the back, it's not always obvious. So you know, that might be, you know, one of your questions, was it a dynamic failure or a gravity failure? This particular failure was associated with a lot of seismicity, including a large event, so I believe it was a burst. So then that brings into another series of questions. How big was the seismic event? How far away was it? In many cases, you'll find a flurry of seismic events, and you might assume it's the biggest one, but maybe it's the 0.5 that was closer rather than the two that magnitude 2 that was further away. Another common observation I've seen is you'll see burst damage, but you won't get a seismic event right where the damage was, and that could be I'll talk more about it, but a coiled spring where you have strain energy concentrated around the opening that gets triggered from a far field big event. And if you think of how a seismic system records a big event, it'll take a few hundred milliseconds, and anything other events happening in as that big wave is coming through, the system's blind to it. So you'll see that often where there's damage somewhere, but not a local event to it, and it may have been triggered from far away. There was a lot of work done in the past on PPV distance, and that's still useful. But and I used to hear a lot of I'm designing for a magnitude 250 meters away. What does that mean? And if you look at this picture, you'll see a lot of damage in the middle of the photo. Just trying to get my mouse to work here. And no damage over here. So, if you have PPV distance, it sort of doesn't really make sense. The other thing is a magnitude 2 might have a source radius of 50 meters. So a magnitude 2 location 50 meters away from the damage is not, it's a bit fuzzy what that really means. It's also, there's a ground motion amplification as that wave hits the surface, as it hits the fracture zone. There's a bunch of different things going on. So the seismic event is semi-quantitative in a sense. Then you're going to look at the ground support performance. You can see here one of the reasons I think it was a burst is we had very high capacity static support that should have held up that amount of material, but static support like shotcrete and rebar is very stiff and has low deformation capacity. So gravity wouldn't necessarily overload that support system, but a dynamic ground motion would. But a lot of work's been done into yielding ground support systems, kind of obvious, I guess, but trying to catch a fastball with a stiff arm, it hurts. So you need deformation capacity. Then you start looking at the support system wasn't adequate for the conditions. What would have worked, and then you can get into the burst mechanisms. Is it a fault slip? A large event, mine-wide fault could generate a mag 2 or something. A local prominent slip that in a big excavation we've seen magnitude 1s off joints. It could be small scale, big scale. Depends how far it is. How much locally stored strain energy? Is it pillar geometry? That black rock in the photo is not a dike. It's actually soft, shaly material included in really stiff, strong material. So, what's the local geology? And, all these things are these questions. And if you really think of putting design to it in terms of capacity and demand, it's not easy to put numbers to all those things. I've probably shown this photo a few hundred times, and I've seen it in a few other presentations, but it's a fairly large burst back in 1999, and Patrick will know where this comes from. Back in 1999, we were looking at putting in rock burst support systems. The first, Dave Headley had put a handbook out on rock bursting in the early 80s, and 1996, the Geomechanics Research Center under Peter Kaiser put a really good handbook out on rock bursting, which is still a good handbook. And Ming and Peter have updated that since. I'll show you a reference to that later. But so this idea of yielding support systems and energy-based kind of design was being touted a lot in the 90s, and South Africa had done a lot of work. But the truth in Canada in 1999, there weren't many yielding bolts on the market. If you phoned up the ground support supplier and said, I want a yielding bolt, he might have scratched his head, and maybe we debond the cable or put a sleeve over part of a rebar, or get a cone bolt from South Africa. But that's really kind of what was out there at the time. The design concepts were there, but the amount of dynamic testing and bolts on the market were pretty limited. So there's a few gaps. So now, if you flash forward to 2026, there's almost I would say an overwhelming supply of different yielding tendons, and for every type of yielding tendon, there's four suppliers with three slight variations to it. So it's a good thing, but it's also a bit overwhelming when you see what's out there today, which overall it's a big improvement since 1999. There's also a lot of different dynamic testing facilities and different numbers. One of the issues is there's not really a clear standardization, so dynamic tests from one country to a next to a rig to another rig aren't all exactly the same. One thing that unfortunately hasn't changed that much, there's a lot of progress, a lot of things out there, but one of the main problems from this burst and most bursts that I've seen since that and before that is a lot of the tendons aren't breaking when you get a rock burst. This is a zoom in the wall, and Dave Ortlip, who's a rock burst expert from South Africa, dubbed these naked tendons, but that's a common theme, especially in hard brittle rock where the rock unravels around the bolt, and so those are low capacity split sets, but we didn't actually get our money's worth. Now in this case you can point to the many things, but like the shotcrete's over top of the bolt instead of the bolt over top of the shotcrete, and it's not a good system, but getting your money's worth out of the bolts is still, in my opinion, one of the biggest problems, and I'll talk more about that. Dynamic testing, I've just showed some photos from the Noranda Technology Center. This test rig has an interesting history, but I won't go into the whole history of it. But Peter Kaiser and Sean Maloney had designed it for Noranda. It was supposed to originally go to Brunswick Mine. It ended up at the Technology Center, and they did a lot of really good work there. And when Noranda Technology Center was closing down, Veronique Felmang got that rig into CanMet in Bell's Corners, and they've been running it since and made many improvements and done a lot of good work. But at the time in 1999, 2001, there wasn't a lot of dynamic testing out there, and I think this is still one of the gaps. Is there's a lot of testing, but if you look at that donut stack of weights with a hole in it, and it's sliding down telescopically over the bolt grouted into a steel tube, it's really a perfect actual hit on that bolt. So it represents sort of an ideal condition. And in a lab, you want ideal conditions and repeatable tests and things to get some real numbers. But the number you get from the lab is not going to be the same as you get in situ underground. In this particular case, there's an electromagnet on top. You turn the power off and the weight comes down, and kaboom. At the time, I got some of the engineers at the Noranda Technology Center. I said I wanted to test a rebar, and they said, "Well, it's going to break." And exactly, we want to have that catastrophic failure of the stiff bolt to show the miners, and then show them what a yielding bolt could do. So, since that time, there's been a lot of excellent testing. Australia led the way for a long time. South Africa, Poland, Sweden, and Canada. I think China has some dynamic testing. So there's a lot of more stuff out there, Switzerland, and a lot more numbers. But at the end of the day, if that test says you get 40 kilojoules out of that bolt, and you put a bolt every square meter and say I get 40 kilojoules per square meter, you're fooling yourself, because we got to figure out a way to cut that value to a field value. I sort of use an analogy of gold mining. If you take the assay from that gold nugget and spread it through the deposit, you think you'll have way more gold than you really do in like mathematically. So they'll cut assay values to something so that, the average comes out better. And, how do we go from an ideal actual impact or pull test in the lab and get a number that's more representative of what we can expect in the field? I think that there's still some thought that needs to be done into that area. This is when I say there's a bewildering amount of bolts out there. This is just a small sample from a paper from John Hadjigeorgiou. I won't go through the details of each bolt and each yielding mechanism. Generally, a lot of the yielding bolts in the market rely on steel stretch, so steel can elongate depending on the type of steel, 10 to 20%. So a meter stretching 15%, that's quite a lot of deformation. And so the steel stretches are kind of a popular way to do it. The original stuff we were using with these modified comb bolts, which was a crib of a South African comb bolt that could, but the paddle on the end could mix resin. One of the issues was that paddle wasn't consistent enough mixing resin, but that's another story. At the end of the day, when you do a pull test on this particular bolt, you'll get a certain result, and then you'll get this low deformation. The area under the curve is good, but when you actually looked at it a little more carefully, the concept of the bolt is to have the cone snowplow through the resin, and when you pulled it statically, you got some cone plowing, but most of it was steel stretch. And then when you hit it in the dynamic test facility in the lab, you got a lot of cone plow and a little bit of steel stretch. So just the point being, uh, static and dynamic aren't always the same depending on the bolt type you're using, and there can be fairly significant differences. Got a couple photos I borrowed from my buddy Blair, but I won't go through the history of this particular bolt. But as you can see, it's been exposed by mining, but a pure axial test on that bolt, there's got a lot of shearing going on, and that's sort of one of the realities in especially hard brittle rock where this is just a picture of a fracture zone exposed in overhand post pillar cut and fill mining. So that would have been the fracture zone in the back, and then you're breasting through the next cut, and you can sort of see what the fractures above your head looked like from the previous cut. Um, this is where there's a bit of an art and some empirical experience required. So if you think of some of the idea of monitoring deformation, so you understand how much load displacement capacity is lost in a bolt. It's not that obvious when there's 102.3 fractures in that first meter. So each fracture is dilating a little bit. So a rebar that can stretch only 2 centimeters, but maybe that rebar is stretching here, 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 here. So it's not the same as localized displacement. So the impact test, the pull test tends to be more or less simulating local displacement, and in stress fractured material, you'll get a zone of displacement, and even between two extensometer points, there's some multiple fractures. So depending on the bolt type, that may or may not matter that much, but it's not the same as locally the pull test, which localizes displacement. There's also a lot of shearing that can go on in these fracture zones before, say, a burst hit. So that pure axial number is not is an optimistic number. I think you could say the pure shear test number maybe be a pessimistic number, but and there's a lot more data on axial testing than shear testing. I think what's nice is there's some work. This I was referring to a paper by Greg Knox and John Hadjigeorgiou, and Charlie Lee in Norway has done a lot of work with shear testing as well. So a lot of that data started coming out, but the point is you're not likely to get that beautiful lab test of the actual drop test that says 40 kilojoules for the bolt in the field. There's a lot of things that can inhibit that. Despite all these complications, we had some excellent success with yielding support systems over the last, 30 years that I've been in the industry. Um, there's a case here, where there's yielding bolts. Those would be cone bolts over snow, load spreading straps, so stiffer straps, hard to punch the plate through. There's some really compliant chain link mesh, and you can see that mesh can balloon out between the bolts and move decimeters. There's another Blair photo here where the mesh can clearly move decimeters unless you entomb it in shotcrete. So obviously, if you entomb the mesh inside shotcrete, it now can only move centimeters, and for a bad burst, you really need decimeters. But anyway, you can see that we've had success on yielding support systems. It's still not that clear what number you can attribute to the bolt. I think it's fair from a simplification point of view on design to say that you can add the capacity of the mesh to your design numbers. As you can see from Blair's photo, that mesh between bolts can balloon out tremendously. So similar to what a pull tested mesh would look like. It's looking at a burst in this particular area. The support system wasn't fully upgraded because it was no longer needed and was just barricaded off. So just observations afterwards in an area that had no exposure to people, but you can just see some things, shotcrete on the outside, brittle eggshell, so it's not going to perform well, and we've known that for a long time. However, it's hard to quantify, but mesh over shotcrete does a lot of good, and I'll talk a bit more about that. But the shotcrete, if it can lock in the stress fractures and around the tunnel, that provides confinement. And beyond the stress fracture zone is where the high stress, the stored energy is. So anytime you can add a bit of confinement, it goes a long way. So it's not so much the confinement of 50 millimeters of shotcrete, but the shotcrete's holding in the fractured rock, which is now a few decimeters of confinement to the high stress beyond it. So that has value. It also has value as sort of a bit of a plate where you get more even loading on the bolts when you mesh over shotcrete than just mesh alone. Hard to put a number to it. You can see here there's these rubber conveyor plates behind the steel plates. There's different ways to prevent screen punching, but that's one. Just from one point before I forget, from a mathematical point of view, trying to do support design, you'll find the demand for a bad burst is something in the order of tens of kilojoules per square meter. Maybe it's 20, 25, 15, but it's in that order. And the capacity of most mesh that we use in mines is more like 5, maybe 10 kilojoules per square meter, something like that. Maybe a little higher, a little lower, but at the end of the day, this unraveling around the tendon is a big problem, because when you start putting the design numbers to it, you need the tendons to do part of the work, a good chunk of the work. When we sort of zoom into this a little bit more closely, just talk about a few things. Weak links, the rubber gasket or a mesh strap or a 30 by 30 centimeter mesh strap or butterfly plate. There's many ways to prevent the square sharp edge plate from punching the mesh, but you'll still see that's a common weak link. I think one of the problems, I know there's different meshes out there, but you get into this sort of whole procurement issue, and why is mesh and rebar cheap? And it's relatively cheap because it comes from the civil engineering industry. Most mesh is used to reinforce concrete somewhere. So when I talk to the supplier, I say, can you add a few strands, weld a couple extra strands underneath where the plate will be, and they're selling 95% of their product to a concrete reinforcement guy in the civil industry. There's a bit of a gap there sometimes. I think there's some simple improvements you could do to prevent some of these weak links. That's my cursing symbol there. Hopefully you only see it symbolically and I won't swear. Another there's Dave Ortlett's Naked Tendon. Again, not a high capacity bolt, but it was easier to unravel around the bolt than to break it. The screen seams. Now we got pretty good overlaps, but at the end of the day, anytime you have a seam, it's going to be a weakness. We'll sometimes put straps over the seams and stitch them together. Roll mesh has advantages because there's fewer seams and it can displace more, but then that's another different process for installation underground. Now that again, the shotcrete on the outside, it becomes part of the fly rock. And then just to reinforce the previous point is, if you start thinking about a magnitude 2, 10, 72 meters away, well, that distance from that big event and that distance from the big event is about the same. But so a PPV distance calculations, there's more to it than that. It's still a good indication of relative shake, and shakedown is a mechanism. So it's not. I'm not saying it's useless. I'm just saying it's not the right sort of numbers to use for the demand side of the equation. I won't talk too much about this. This is a close call. We're really fortunate no one got hurt. Happened in 2011. Topic for another webinar or another time is mine design. This is the point where you've got to remember, I'm talking about ground support, but it is the last line of defense. It's never an excuse for risky designs. And I don't know how many mining engineers have had to sort of elbow smash and say, no, we can't do that. And they'll say, well, we'll just put rock burst support in there and then we can do it. No, you want to have a good design first and have a good last line of defense as well. And this is a case, again, this happened in 2011. And since that time, it was a narrow vein operation with a lot of converging mining fronts. And they basically allowed some of the mining fronts to converge too much and too much stress going through too small a window, and implemented a rule it's very dependent on site specific rule. So depends on your strength of rock and how deep you are and a bunch of things. But we found by leaving the minimum of 4 cuts or 12 vertical meters, our converging mining fronts, we switched them into a long hole blast hole method, and we dramatically reduced the number of bursts at that site. So letting the converging mining front shrink too much is really we can talk about the ground support here, but at the end of the day, I think the mine design was really the bigger thing to fix. So just as a reminder on that. I've talked a bit about this, but one of the quandaries for deep mining, if you think of mining 101, you train underground workers to scale out loose. In the context of hard, brittle rock at depth, you're scaling out the confinement that's protecting you from the high stress right beyond the yielded zone. So if you peel that out, your strain burst risk will go up, and that process might just start again. However, that's part of the art of ground control. Is in this case, the fractures are tight and haven't dilated much, so locking it in with ground support's a good thing. If you've let it loosen up too much, or if it's gotten too deep and it becomes a point where you need to take it out and take it down, and it's not always obvious. There's a really nice case study that Alex Hall's done for the Onaping depth shaft sinking, where the fellows were over mucking the shaft bench too much and peeling out the fractured material. And then we had strain bursting problems in the bench. And anyway, there's a couple of nice papers on that. But the old school mining of scale out the loose is kind of takes a slightly different meaning at depth, because you're scaling out the confinement. This is that same 1999 burst, but it was a pillar geometry. So just turn the picture sort of 90 degrees. Not in hard brittle rock, one simple design sort of methodology is to look at the weight of the fracture zone and assume it gets spit out at a certain velocity, and that's kind of the approach that I use. But there's a lot more to it, and when you assume a velocity, it's v squared. It's not perfect, but anyway, sometimes a simple way of looking at it's not a bad way. At least get you in the right ballpark. Back to just what the shotcrete do, and this is some nice testing that Ming had organized for us. And what it shows is the old story, a little bit of confinement goes a long way. So if that bit of shotcrete can confine the fracture zone around the opening, then you really make things a lot stronger. So what we had this issue at Onaping. We're sinking a shaft in hard brittle rock at 2,500 meters. And if you think of sinking a shaft, well, you're not slinging a scoop down and a jumbo down and a mechanized bolter down the shaft barrel to start mechanized. You have to get a footprint first. So there's a stage where you have people on handheld equipment bolting. And so what we did is shot first and ask questions later. So adding, high early shotcrete, thin coat, and they were bolting through it within an hour, confining keeping the fracture zone in place, and you dramatically reduce the strain burst risk and made it a lot safer for that, what would be on paper a high risk activity of using handheld bolting at 2,500 meters in brittle rock. But anyway, they're just practical application. The other part to the story would in deep hard brittle rock is there's a time component, and I kind of get frustrated sometimes with mining people because you have a metric of how many blasts did you get this week? You didn't get your blast this week, and well, you have to bolt it too. The longer you leave that deep tunnel unsupported, the more that fracture zone loosens and dilates, and the more scaling you do, to bolt it. So, it takes the longest part of the cycle is bolting, but if you've left the high stress fracturing opening open for 3 or 4 days and you scale out 10 tons, yes, it's going to take you a lot longer to bolt than if you lock it in place and get to it a lot earlier. So there's definitely that's a bit of an art, but there's definitely a time component even in hard brittle rock. Obviously in salt and squeezing ground, that they're well known time dependency, but even in hard rock at depth, that's part of the story. Um, different rock masses. Again, I'm biased by my experience in hard, brittle, massive rock, but we also deal with some jointed rock. In this case, there's pros and cons. Sorry, going too far. The obvious problem here is wedges, and at depth, you always have to, worry about static ground support design and holding up a wedge. The pro is all these prominent joints in this norite rock type. They also displace, shift, and shimmy a little bit with the stress redistribution around the tunnel, and you don't get as much stored strain energy. So the coiled spring is not as bad, but you can have some pretty decent wedges. So it's a bit of a pro and a bit of a con. But we have found a bit more success with yielding support systems in the jointed rock because part of that joint displacement and dilation takes up some of the blow, and it's also not a bad way to transfer load to the bolt. So you've got stress fracturing, bulking, and things going on, but you also have dilation in joints. And if you think of a joint opening up and a yielding bolt that goes across it's not a bad load transfer mechanism. So we've had reasonably good success with some fairly large magnitude events in this jointed ground with rock burst support. You see, this is an early trial of those rubber conveyor washers behind the plates, and then this would be a 30 centimeter by 30 centimeter mesh strap plate. The problem with these strap plates is if you're using a mechanized bolter like a row bolter or a bolt tech with a carousel, that the strap doesn't fit into the carousel where the smaller washer does. We're also using 200 millimeter round plates with a beveled edge in these carousel style bolters, and that seems to work reasonably well. Especially that bevel edge doesn't cut through the meshes easily. The more massive ground, I mean, we've had success ground support in this type of rock. Obviously here you can see, shotcrete and rebar relatively widely spaced didn't work too well, but you do get more of that unraveling and a shotgun blast. In this case, the a dike fragment in the upper corner spit across the drift, hit the mesh here and dropped. So those are really difficult to support and get really good load transfer to the tendon. You're more likely to get a naked tendon in this type of ground than in the more jointed ground. Um, I haven't had a lot of personal experience in high deformation or squeezing ground, but I always love talking to the people like guys from LaRonde and Westwood and other mining camps where they have squeezing issues, because you can really sort of see what deformation capacity and different ground support types, how it works. In bursting ground, you might not see any movement until it bursts, so you could have a few kilometers of tunnels supported, and then year 3 of mining, you get your first burst, and then you see how it works. Where with squeezing ground, you put it in this week, and you can sort of see how it's going to work by next week, kind of thing. You see the top bolt is punching the plate, and the bottom one's going for the ride, and that top one's a steel stretch bolt. So the steel does stretch and plastically elongate and elastically move, but in the drop test rig in the lab, you'll get that whole area under the curve, and it'll be really nice, but it's pretty stiff. It takes it only starts to stretch at very high load, so you can get things like nuts punching the plates, and where the softer bolt that's not as good to hold up the wedge, but what goes for the ride easier it's a comb plow bolt, and it's going along merrily for the ride. That sort of quandary there is steel stretch bolts. We use them, and they're popular because they fit a lot of static design criteria, because they're high capacity and fairly stiff bolts, so they hold things together, and they can stretch if dynamically loaded. But sometimes I think a little bit softer bolt that can go for the ride easier may be something we need to look at when you get into more severe loading conditions at deeper mines. Excavation vulnerability, obviously we could talk a lot more about this, but it's a huge factor. If you let too big a span with too big a fracture zone dilate and loosen up, and then you become vulnerable to fall of ground, and seismic shake damage. So that dynamic wave, it does a bunch of things. The floor goes up, the back comes down as the pulse goes through. You lose clamping forces. So if you got a steep wedge and you were relying on natural horizontal stress to hold it in, so things you can do things to reduce the vulnerability by design. Maybe you shouldn't have opened up so much ground in the first place, but if you've got a big wide area, a shotcrete post is an excellent way of breaking that span. However, it's all a classic case of rigid support and where you need deformation capacity. This particular post on the right, I think it had north of 3,000 tons capacity, but it didn't have a lot of displacement capacity. And as the wave went through, the post got crunched. It's going to talk to purge or not to purge. There's a bit of an art there. If it's in the back and the ground's loosened up and it's ugly, you might have to take it out. Sometimes you have a choice. In this case, it was a narrow vein. We decided not to mine this vein going up, and then plans changed. Oh, we're going to mine it. But at the time, we filled it full of waste, and we had a burst hit by this intersection, and we mucked it out later because we decided to mine the vein. And you can see how the wall had bulked out. And so you're in a vulnerable place near an intersection now. And if you had scraped it all out, then you've just made a vulnerable place more vulnerable. So we were able to shotcrete over it, pump resin till the cows came home, and cable it back. And at least, so sometimes if you can keep that confinement and preserve that span in this case, then that can be, an advantage. Although the operators were cursing me because they pumped a lot of resin into that fractured ground before they could get the bolts to set. Case where it's better to take it out than to leave it and try to rehab it. In this case, TDB stands for take down the back, so kind of like a cut and fill style. These are 15-meter wide panels, so there's 1, 2, 3, 4, 5, so 75-meter flat abutment. This blue stope would have been better to have, high lifted it and dropped down below, but at the end of the day, it wasn't. And late in the mine life, hey, can we go get that stope? And so do you go into this original overcut here and try to drill upwards into that, knowing that this big flat abutment had a lot of seismicity and a lot of history to it? Or do you say, oh, I got to scrape that out and re-support it and take it down, the dilated material down? And that's what we did, and we safely extracted the stope. So there's some decisions you have to make, and you can use numerical models to sort of make some forecasts and seismic modeling to look at actuals. In this case, I don't have the figures on the seismicity, but there was a bit of a location error problem in that area. So trying to determine if you have 5 to 10 meter fracture zone based on being seismically active originally, and then the seismicity migrating away, and now it's a dead zone seismically. That's a very good telltale sign. But when you have 10-meter location error and you're trying to resolve something on this scale of 10 meters, then it's not always, it's a bit fuzzy. So anyway, when you start, I'm just showing a couple photos, but when we coming over the back of that original crosscut, you can see how dilated and busted up that ground was, and the depth of fracturing was higher than the TDB, and it was just a lot better, safer to take it out than to try to pin it in place. You can imagine trying to bolt through this, and especially cartridge resin, which the resin goes into the dilated cracks, and you're not filling the hole. The pumpable resin is really good for that because it'll only migrate in an open crack maybe half a meter from the whole original hole. But even still, it's sometimes you got to make a choice, and the better choice could be scrape it out and resupport at the expense of losing that confinement. So there's a lot of design methodologies out there. These are two books that I would encourage everyone to read. I'm talking about ground support in a lunch hour webinar, and there's obviously full-blown textbooks on the subject, so there's a lot to it. There's the methodologies and probabilistic ground support design, factors of safety. There's a bunch of approaches to take, but I think at the end of the day, despite really good work and good methodologies, you still have to accept that it isn't exact or perfect. It's kind of a ballparking exercise that gets you in the right bandwidth, and you do have to make some assumptions, and it's the process you need to do, but demand can be a combination of locally stored strain energy, far field ground motion, near field rupture. It could be momentary loss of clamping forces. There's a bunch of ground motion amplifications, a bunch of things going on that are hard to put solid numbers to on the demand side. On the capacity side, axial test and shearing in the field, and load transfer to the tendon, and all those things, that's a bit fuzzy. And at the end of the day, you still need to have some empirical experience or an observational approach to ground any sort of design numbers you come up with. So back to, do you use a simple model, or do you go down a little more elaborate sort of methodology? But there's pros and cons in this particular simple model, where you say, I think the fracture zone will get spit out at X number of meters a second. That's clearly a bias towards hard brittle rock with stress fracture around the opening, and stored strain energy just beyond it, and might not be appropriate for, say, buckling of a stiff layer or something. But anyway, there's different approaches. I think I'm really kind of encouraged with some of this recent shear testing from Greg Knox and Charlie Lee and company, and so how do you cap that number of what a bolt can really do? And shearing's maybe pessimistic, but the area under this curve is probably a better design number than the area under that curve. That's very optimistic, and that's maybe a bit pessimistic, but at least I think we're kind of converging on places where we can get a little bit better guess, make some more sound assumptions in the design. Again, some really good work from Min Kai and Peter Kaiser, Alan Moss, and company, and there's a lot of wisdom buried in those methods. But you still, at the end of the day, have to make some assumptions. And I think just a few final thoughts before I take some questions. But there's a lot of choices out there versus 30 years ago. I think there's a bit more thought needs to be put into trying to preserve the rock mass strength. So, does rebar have a place? Well, if you put a rebar in the bursting area and the nut flies off, it can be like a bullet. But if you had, a rebar inside the rock reinforcing and resisting dilation, there's some value to that, preserving the rock strength. Shotcrete on the rock helps. Shotcrete on the outside is a hindrance. So but at the end of the day, shotcrete's very expensive. So it's fine to say I'm going to spray everywhere and mesh over it, but it's expensive to do that. So you have to sort of justify when and where you do that. I think the industry preference to keep it simple and have one bolt do everything might be a bit optimistic as we keep going deeper into more challenging environments. But anyway, hopefully, you got a few ideas from my presentation, and be happy to take some questions. It's always tough, these webinars, because you can't read the room. You're staring at your screen.
We can see your calendar now, Brad.
Oh.
Are there any questions for Brad? Yeah, okay. Please keep sharing, keep raising your hands. Damadora.
Brad, you want to put back your PowerPoint just so that you can navigate through it as you're being asked questions?
Okay, sure.
I see a hand being raised by Damodara.
Yeah. Hi, good. Hi, Brad. Great presentation as usual.
Thanks.
You were referring to that shear testing results, but I see only the load versus displacement. Did you see any energy results there? Like now, what was the impact?
In this case, the most of the shear testing that I've seen is done in I was just trying to find it there. Sorry, in this static kind of environment. So,
okay.
It's I think there's some thought being put into sort of dynamic shear tests, but at the end of the day, that's pretty tricky to do.
Okay.
You can see like the actual load doesn't necessarily change that much, the maximum load capacity on the bolt, but the deformation capacity clearly is a lot less.
Okay.
So there's a lot less stuff in the literature on shear testing than axial testing. So I think it's a gap that's starting to get filled, but it's still a gap in my mind.
Okay.
If you have especially with the number of bolts out there, if you say I got my X bolt, where's my shear testing? And well, the guys haven't caught up with all the different. Although so the work that Greg Knox has done recently has been very good, and they've done quite a few bolts, but there's so many tendons out there that we haven't. There's not numbers for everything for sure.
Yeah. Okay. Thanks.
Okay, next question, Yang Yong Chen.
Okay, this is Jason Walk at Red Lake Mine. Thanks a lot, Simser, give us this good presentation and bring me a lot of good memory as well. I remember when I first started in this industry, there's an engineer, her name is Veronique Fahmat. She hired me, and at that time he's transferred to Kemet. That was your mention, the dynamic test there. She asked me to do some calculation of the energy absorption. I think we use the mathematics. You could use MATLAB as well, but that's where I started my career. So that hold my memory very well. For the so I saw a lot of picture. Those days it's very close to our operation as well. So in the presentation, you mentioned the PPV there. I just want to comment a little because I attend a lot of mine. It's lateral vein mine. It's like longitudinal mining. When you blast the stope, like along the drift, it's just like the blaster. It's perpendicular to your drift, kind of this. Then even you have very high PPV, the brow or the ground that surround the close to the drift, it damage very little. Most of the time, it's. However, if you have opportunity, you have a blast like a parallel to your drift, like if your drift is parallel to your blaster side, and then the damage is way heavier. So that probably give us some hint, like the PPV when they transmit, if the direction, if the direction is against the void, like towards your void, your drift, you probably have much more damage because the ground support is mesh and the boat. But if the PPV is along your drift, then you probably have very little because the major support is supported by the rock itself. It's elastic just transfer of the wave, and also the other one is as Peter Cass and Min said in their book, the dynamic energy created is equal to 0.5 times mv square. V you could use PPV. M is mass of your loose material there. So if your ground support is in very good rock, like there is not much loose material behind the mesh or a shotcrete, the ground support can subject very high PPV. We have done some tests.
I'm sorry. We have other questions too. Do you wanna?
Okay.
You wanna say your question? It's if I understand right, the question is on the orientation of the opening, and how can that influence the behavior of the rock mass under seismic loading?
Yeah. Just add one sentence. It's if it's very good rock and there is no loose of material, you can really subject high PPV because it's shake together. It's not really stretch the boat.
Would you like to comment on that?
I'll just maybe say something quickly. There's a couple ways to look at it. I think the ground motions. It's not the rock dropping in the calm pond and the perfect radiation pattern. The seismic events, there's a direction to them, and it's a lot more complicated. And the excavation vulnerability which includes orientation, has a lot to do with it. So all those things that's part of the complication. I think at the end of the day, the stuff from say 30 years ago, where a lot of people were talking about magnitude and distance. How do you explain? You can't explain 4 and 5 by any kind of magnitude distance relationship, if you know what I mean. It's 5 has no damage and 4 has a lot of damage, or 3's got even more. But all those things are factors. I think the PPV type of stuff is a component for sure. There's refractions and reflections around the opening that amplify the PPV, so that your seismic sensor, you want to put the sensor in solid rock into the rock mass, but when you put a sensor on the surface and one 3 meters in the ground, for example, you'll see a huge difference in the amplitude of the waveforms, especially at high frequencies and even at low frequencies. So all that's a component of it. I think in our hard brittle rock, it's still a relatively small component of the overall issue. Is, we see damage that's clearly meters per second, and the PPV sort of maybe centimeters a second. So it has an influence, but it's maybe not the biggest influencing factor. But like say, orientation does matter for sure, and as does the condition around the opening, the vulnerability, all those things. So it gets a bit complicated for sure.
Okay, thanks.
There's another question here. Has there been any research on long-term performance of the support systems, for example, post-abandonment?
Yeah, I think that's a area that's needs to be a bit more thought put into it. So, for example, there's some fantastic work done in Switzerland where they'll put a whole support system in, and they drop this big ass weight in from a quarry and drop it from big height and smack the whole system, and then they'll measure the how much load the bolts took versus how much the containment system took, and some really good information. But at the end of the day, it doesn't tell you anything about the loading history of that tunnel. So in a deep mine near stoping, the loading history over time makes a huge difference. And I think that's where mine design, obviously is a big part of it, where why are you asking an access to stay open and very high stress over 5 years or something? Maybe you gotta think about getting in there, getting out of there, and not keeping an artery open too long near high mining induced stress. I think I haven't talked about this, but at some stage, I think numerical modeling, it's not maybe not quite there, but there's so much of this loading history around the opening, and the complexity of the fracture zone and shearing, all this stuff going on. I think modeling will ultimately be the best tool to sort of answer some of these questions, but it's maybe the run times on some of these bounded block models and things like that now are a bit prohibitive. But I can sort of see that as a path in the future to take that into account. But clearly, a tunnel that's been in a high stress situation for a long time, and then get hit in year 5 or something, that can be a big problem. It's capacity of the support that gets used up over time. It's the shearing that goes on that kinks things. It's a whole bunch of stuff, and it's also just that loss of rock, the inherent rock mass strength as it continues to get damaged and dilate. You lose some, the strength. You're trying to help the rock support itself, but the more punishing environment you put it in for the longer, like an abutment area of that just keeps getting higher and higher stress over time. By design, you should maybe get the hell out of Dodge sooner, kind of thing, because it's hard to keep those things open for too long and too difficult a situation.
There are 2 questions on cable bolts. Do cable bolts play a role in ground support with rock burst prone areas? And what is your experience using bolt cables?
Yeah, so I'm very I'm not convinced about plain cables. I've seen too many stripped cables in too many situations, and I think so. Even though a bulge makes the cable stiffer and has less deformation capacity, I think it's still important. We're using a pumpable resin process for cables, so the friction of that material versus grout is a lot less, and so I'd be very worried about putting a plain cable. It's more of a friction support in with pumpable resin. I'd like to use. So we use bulge cables only for that reason. I think it's still, at the end of the day, if you can tie things back with deeper anchorage, it has a role. I've done some dynamic testing back, 30 years ago, 25 years ago, I guess now on cables, and you get reasonable numbers from the drop test on a cable. So anytime you have better surface support, so I'm a big fan of plating cables. I know there was a wave, not, you really need to plate cables, but anytime you can have better surface support and better load transfer, so I would advocate plating all cables for sure. And they do play a role in space, wider spans. You definitely need to get in deeper. They're so they're part and parcel of a ground support system, and they add benefit dynamically as well for sure.
Amodara, you have a question?
Yeah, it's not a question. Just I have a comment. I heard Brad mentioning about the Switzerland, the dynamic tests and the ground support system. I was part of the couple of tests, Brad, in 2023 and 2024. What we observed was majority only one bolt, the central bolt, was taking the load. All the surrounding bolts was hardly any transfer to those bolts. That's what data was showing. I'm sure in the field, the system will definitely behave differently.
Yeah, and I don't want to criticize those tests. I think I'm a big fan of the dynamic testing in general. I think we've learned a lot from it. One of the reasons we have so many choices on bolt types is because of these testing programs, has been able to, prove out some concepts, and so it helps us, see how things perform, but it's not the same as the field, but it adds good value, but there's still you gotta get your boots underground and have those observations as well.
Yep. Thank you.
Maybe Nicholas, you have a question?
Hi, thanks for the presentation, Brad. I have a quick question on kind of, if you have a support system that's already working, when is the right time to kind of try something new out?
Yeah, that's a good question. I think it's tricky because I'm used to, say, we have a lot of experience from Nickel Rim South mine, and we started stoping in 2009 and finished. The mine's been on care and maintenance since 2024. So if you look at the history of bursting in that mine, really we didn't see much until about 4 years of extraction. So you could argue, based on the first 3 or 4 years of mine life, that fibercrete and widely spaced rebar was perfectly adequate. But as the extraction built up, and you've built up abutment stresses, you've converging mining fronts, you've also pierced faults over a bigger mining area, and now that fault can slip over a bigger area, which means potentially bigger events. So all those things kind of escalate with time, and so if it's what you have is working today, you do have to kind of crystal ball, and numerical modeling, if it's done well, can be a good forecasting tool to give you at least a relative idea of how much more difficult things will get. You may be, in Sudbury, if you're 500 meters below surface, it's very good rock, it's very forgiving. At 2,500 meters below surface, it's still very good rock, but it's a less forgiving environment. So there's a whole bunch of things that kind of come into it. But it is, I do recall being at Nickel Rim when it was a project in 2007, and I'm looking around and seeing all this fibercrete and rebar, and the guys are really happy with it. And I thought, oh boy, how long is that really going to last? And the answer was 2 or 3 years of mining. We started to see cracking in the shotcrete near the stoping areas, and then it was all, we needed to upgrade, sort of thing. And so so it's not necessarily a simple question, but if you can forecast the future with say a numerical model or something like that, and then see that, oh boy, our stiff conventional support system's working great today, but I don't see how that's going to work in the future, then it's time to sort of it'd be better, you obviously want to be proactive about it, but mining tends to be a bit reactive sometimes. It was at a mine where it kind of became a bit of a shotcrete orgy for a while, and it seemed to be the elixir for all ground control problems until we started getting bursting, and then it was part of the fly rock, and we had to do a lot of band-aids over top of it. So it's not always an easy question to answer, but if you can be proactive and sort of forecast the future, then make some changes accordingly rather than being reactive. It's a good idea for sure.
Yeah, receiving more questions and we're running out of time. Maybe 2 more questions. Wei, do you have a question? We can't hear you.
Thank you, Brian, for the great presentation. I have a question about the shotcrete. You talk about the shotcrete is really costly and it stiffens up when under the dynamic loading. In your experience, do you see there are some potential ways, let's say from the material side, to reduce the cost and even kind of, somehow reduce the stiffening issue? I would like to hear from you. Thank you.
Yeah, it's a good question. If cost was not an issue, of course it is, but if it wasn't, in our hard brittle rock, I would shoot everything with a layer of shotcrete and then mesh over top of it. I think it's a nice way to support the ground. The only reason we don't do it everywhere is kind of a logistics and cost issue, and so we try to do that selectively. So if it was easier and cheaper to use in higher volumes, then that we would. I think I don't know that you can really change the material properties that much. You can add fiber and you can add longer fibers and change the aggregates and stuff. But at the end of the day, what shotcrete does well is it's resistant to blast damage. The problem there is now you have it on the outside, so you're protecting from fly rock damage and multi-stage excavations, but now you have the brittle layer on the outside. But the stiffness and strength of it is what preserves the confinement and holds things together nicely. You just can't rely on it for dynamic loading later. So the mesh over shotcrete is just a really nice way to do it. I don't know that I would change the properties of shotcrete because it has a lot of practical uses as is. But just as you can see from the photo on the screen, as the outer layer, it's not the best in high deformation sort of environments. However, with the mesh over top of it, if it breaks up a bit, doesn't really matter. It's contained by the mesh and it's still adding value. So it's one of those things. It'd be nice to put a little bit better of a business case to using it more, but yeah, it's a little bit of a damned if you do, damned if you don't in some cases, especially in a multi-stage big excavation where you have to you get fly rock damage and equipment damage, and then, well, how do you prevent that? You shotcrete over the mesh, and then now you're vulnerable to strain bursting and bursting type of issues. So I probably didn't answer the question well, but
Thank you. Yeah, thanks so much.
Maybe last question, Fedilberto.
Thank you very much for this great presentation. I will need to review it to grasp all the information. I just had 2 questions, if possible. The first one is, what is your opinion regarding hydraulic fracturing and distressing techniques to decrease support demand? And the second question, as for mine design, have you tested different large-scale drift geometries to assess their influence to decrease support demand? Or do you have any thought about what you believe would be an ideal drift geometry if you could create it without any problem? Thank you.
yeah, so I guess the de-stressing, I think if it's done well, it can be very valuable. I don't think it's always done well in lateral development. We had a lot of success with preconditioning or de-stress holes in the shaft sinking environment, where we had problems with the bench face, strain bursting. And Alex Hall did a lot of really good work there. And again, encourage you to read some of the papers he's put on it. But one of the things in the shaft environment, you had vertical holes ahead of the face. And even I know how to stem a vertical hole. You can just pour gravel down it, and so the stemming works really well. In lateral preconditioning, but with jumbo holes around the drift, it's one is you got to know where you're putting the hole. You don't want to put it in the fracture zone. You want to put it where the strain energy is going to be, just outside the fracture zone. And two, it's a lot of that energy just rifles out the collar of the hole. So really need to put some thought into effective stemming, which is it's not non-trivial in a flat hole. But if it's done well, it can. And Alex's case from the shaft sink has some really good quantitative results that show that it did a lot of good and reduced the strain bursting dramatically. Hydraulic fracturing, I think, in the cave world, block caves, there's a lot of work done in, preconditioning stronger rock masses so they cave more readily and less violently is sort of a proven concept there. It's tricky in this sort of really strong rock that we're dealing with in Sudbury. I know Vale are doing some interesting work on that, but at the end of the day, you'll get things like borehole notching, and now you got to get a packer system that seals the borehole that's not got the classic notching in it, and build up enough pressure to do significant enough damage. But if you can damage the rock enough with, say, the hydraulic fracturing, then it won't store as much energy. So conceptually it makes sense. Practically it's not trivial to to get it to work to work. But anytime you put flaws in the rock, it won't store as much strain energy locally, and it's a good thing in terms of managing bursting risk. Shapes of excavations, we don't do that much. I know there's a bit of a tough call sometimes between flat back and arch back. Conventional thinking is arch back's always more stable, but if you get into this case where you don't fracture enough around the opening and you keep the stress near the skin of the opening, maybe flat back's better in that scenario. And if you're deep enough that you're going to get enough fraction around the opening, even with arch back, then arch back's better, is less dead weight on the. So it's a bunch of factors. I will say one thing about the amount of fraction around the opening. When you think of things like mechanical cutting, so a raise bore, it's got a very nice shape for stress flow around it, but it doesn't do much damage to the rock around it either. And you kind of in hard brittle ground, you're sort of engineering strain bursts by mechanically cutting. So it's the opposite of, say, the de-stress preconditioning is you're not putting any damage to the rock, and then the stress is really near the skin of the opening, and so a raised bore at depth is full of strain bursts. It's just that's a non-entry method, so it's perfectly okay. But the rock we record lots of seismicity and see a lot of stress slabbing at depth with the perfect shape. So there's things to be said about all that, but it can, it depends on the rock type and the environment, and there's a bunch of factors that kind of come into it.
Well, thank you, Brad. Thank you for your great presentation and for sharing your knowledge. This is the end of the webinar. Thank you all for attending. Have a wonderful day.
Thank you, everyone, for your time. Appreciate it.
Thank you, Brad.
Thank you, Brad.
Thank you.
Brad.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, Rod. Thank you.
Thank you.
Thank you.
Thank you.
Very good.